Okay, let's take a look at introductions to limits. Here we have a definition of a limit, which doesn't read so well until we kind of put a view of a graph of what they're really talking about here. A lot of people would mistakenly say, if I asked what this is, they would say this is a function. But f of x equals 3x minus 2 is a function. F of x is just a height of a graph at a chosen value x. It's really just a y value. If we're going to think of it as the height, this definition says if the height becomes close to a unique number L, let's say, for instance, that unique number is 5. If the height becomes close to a unique number 5, as x approaches c, let's say that c is 3. So let's go back to the beginning. If the height becomes close to 5 as x approaches c from either both sides, so we're approaching 5 as the height approaches 5 as we move to the right and left toward 3. The limit of f as x approaches 3 is 5 and is written this way: the limit of f of x as x approaches 3 is 5. So we are approaching 5 by time we get to 3. And I don't care what's happening anywhere else on here. From either side, we're approaching 5, a height of 5, at x equals 3. Then we would say the limit as x approaches 3 is 5. Note that we could have a hole in the graph at that point. And not only that, so as the graph's drawn right now, this graph doesn't even exist at 3, and yet it has a limit of 5 because we are in right-hand, left-hand consensus at 3. They both say, hey, you're trying to be 5, we can tell. I don't have any disagreement between my right hand and my left hand. Maybe more interestingly, perhaps f of 3 is actually just a lone dot down here of negative 2. So it's possible that f of 3 could equal negative 2, but the limit of f of x as x approaches 3 could still be 5. Kind of interesting. And that happens a lot where we have holes in graphs or jumps in graphs, and that becomes a very, very important concept as you move on to your calculus studies. So there's our definition of a limit, hopefully broken into a way that you can have some visualization of what it's talking about. All right, let's move on here. Okay, hopefully we recognize this guy as a piecewise function. And if you know me at all, you know that I like to have visuals of what's going on here. So I'm going to just draw this as a factory or a function machine where we put something into this factory, and typically we just get something out. But in this case, my little elves in the factory here are doing a couple things for us. We got a little sentry elf here, stands in here and checks what's coming in here. And if a 3 comes in there, he's going to treat that differently than if a negative 2 comes in here based on their values. We're either going to take 8 minus what comes in there squared, or we're going to take what comes in there and add 2 to it. So perhaps we're just going to, in the case that x is less than or equal to, we're going to treat it that way. But if x is bigger than 2, we're going to send it down to this conveyor belt. If x is bigger than 2, and we're going to treat it that way. But since we're interested in the limit as x approaches 2, I'm going to start with just 2. And if 2 comes into my little elf here, it's going to here because 2 is less than or equal to 2. And I see that if I'm going there, what I'm supposed to do is take the 2, square it, subtract that from 8, and I get 4. So 2 maps to 4, and it exists. And I should have drawn that in green. Easy enough. And then I don't want to put values bigger than 2 onto my green conveyor belt. So I'm going to move to the left. I'm going to choose 1. And when I put 1 in for x squared here, I get 8 minus 1, 7. And when I put 0 in, I get 8. And when I put negative 1 in, it's just like putting 1 in. And when I put negative 2 in, it's just like putting 2 in. And one more for good measure, when I put 3 in here, I get 8 minus 3 squared, 9. 8 minus 9, negative 1. This is trying to look like this parabola to the left. Then I'm going to start the other function, maybe surprisingly, by starting at 2, but I'm not going to put a dot where that is. I'm going to put a circle. So when I put 2 in, this guy says, nope, you're going down here to this function, and I'm going to add 2 to you. I get 4 coincidentally. So 2 maps to 4, but we can't quite touch it. That's why I'm using a circle. Somewhat coincidental that ended up being the same point. Let's continue from there. I'm going to put 3 in. 3's coming down here. 3 plus 2, 5. Put in 4. 4 plus 2, 6, 7, 8. This thing wants to look like a line going in that direction. And we are asked what's happening, what is the limit as x approaches 2? And as you can see from the left and from the right, they are in consensus here that, hey, we both agree. As we get close to 2, we're going to be 4. So we would say that the limit, if this is f, and it is, of f of x, as x approaches 2, is in fact 4 due to that consensus. It's kind of fun. Okay, there are a bunch of rules that explain what we're going to do here, but this is one of those fun sets of rules where if you weren't given rules and you just had to guess, make a reasonable guess, you would actually end up with the right answer. Let's take a look at this. This says some function called f, as x approaches c, it becomes 5. Some function g, this is important, x also approaching c, it is trying to become negative 2. So then we're to find a bunch of limits of these guys that are all approaching c. That's important. So the beauty of this is, I would suggest if you were to guess this, you would say, well, the limit of f of x plus g of x squared, wouldn't it be nice if that was just our limit of f of x at c, 5, plus our limit of g of x at c, negative 2 squared. And isn't it great that that is in fact something you can do? Likewise, b, wouldn't it be great if we could just say that the limit as x approaches c of 6 times f of x times g of x would be 6 times the limit of f of x as x approaches c, 5, times g of x as g approaches c, negative 2. And it is. And likewise, I don't know why I have an A here. This should be C. This should be D. I do know why I have those there. Wouldn't it be nice if we could just say that the limit of 5g of x on 4 f of x as x approaches c is 5 times the limit of g as it approaches c on 4 times the limit of f as it approaches, or negative 1/2. It is. And likewise on what's now called problem D, the limit as x approaches c of 1 on square root f of x. Wouldn't it be nice if that was just 1 on the square root of the limit as f of x as x approaches c, 5, and it is. For those of you old schoolers that are watching this, of course we would write this like that. But what a nice set of rules when it's just so what we might expect the rule to state. Okay, and one last one. If we have an idea what a graph looks like, and I've got an idea what this graph looks like, it's a rational function. Perhaps there's some vertical asymptote or 2 if this x squared plus 2x plus 3 can in fact equal 0. But when I'm looking at this, 4 is maybe not a particularly interesting point on that graph. And I know that rational functions, other than when they cross asymptotes, are smooth and connected. And when I put 4 into this function, I get 3, and I can clearly tell when I put 4 in, I don't get 0 in the denominator. So 4, I'm going to claim on this rational function, whatever it looks like, is just a passing through point. This is called direct substitution. It's probably the first thing we should always try, especially if we have an idea what the family of graphs, in this case rational functions, looks like. So I put in 4, direct substitution. And I get 3 on, let's see, 16 and 8, 24, 27, or 1/9. And direct substitution yields that this is 1/9. And you may be asking, do we know that that's the right hand and left hand behavior as it's approaching 1/9 from the left and right? And I'm going to claim yes, because I have a background in graphing rational functions. And the only time there's a jump and they're not in consensus is when we cross an asymptote. And there is most definitely not an asymptote at 4. So the limit of f of x as x approaches 4 is 1/9.